Hi, this is the first video that I am going to teach you Introductory Linear Algebra. The level of my presentation is at the level of this book, Basic Linear Algebra, written by Blyth and Robertson, second edition, and this is a Springer Undergraduate Mathematics series book. So the level and the presentation of this series of lectures from the book is mainly suitable for those math major students who are doing their bachelor's degree in mathematics or related subjects. So the order of chapters and material that I present here fits exactly with the same order as in this book. But of course, sometimes to make things more clear, I need to expand some parts from theory point of view and as well as problems point of view. But I will keep the level as the level of an introductory course in linear algebra. By an introductory linear algebra course, I mean that I will never talk about vector spaces with infinitely many dimensions. We will not touch Hilbert spaces, Banach spaces. So they might be the topic for another course. But here, even though I will expand the theory, but I will maintain the same level as an introductory course in linear algebra. And I also emphasize on problem solving skills to improve your problem solving skills. This is why below the video you will find a link that will take you to a PDF file containing some problems that I think it would be suitable if you work on them on your own, and then after this lecture is covered. So after each lecture is covered, you will find a set of problems that you can work and solve those problems based on the material covered in that particular lecture. Then for the next video, I will solve those problems in full detail, explain everything around them, and then that would be the topic of the next video. And this alternating way of doing lectures and tutorials will continue. Sometimes each lecture will be accompanied with more than one tutorial sessions, and the reason is that might be there are some more interesting problems that I think and I want to share it with you. It would be interesting if you can also see them and try to solve them. Okay, so now let us start the lesson. The first thing that I want to talk about in this chapter is the definition of a matrix. What is a matrix? So definition. Let m and n be positive integers. A rectangular array of numbers consisting of m rows and n columns is called an m by n matrix, or a matrix of order or size m by n. So this is the way that we denote this matrix. M refers to the number of rows. This is very important by convention in matrix theory. This first number refers to the number of rows, and n refers to the number of columns. Okay? The numbers in a matrix are called elements, or I prefer to use the word entries of that matrix. Okay. And then usually in math literature, people use the capital English letters, capital letters coming from English alphabet to denote matrices. Of course, this is not a universal convention. For example, in physics literature, you can see that sometimes they use lowercase letters, Greek letters for denoting matrices. I will give you some example today. Anyway, now let me write some examples for you. These are examples of matrices. Yes. So for example, I can have this rectangular array 1, 2, 3, 4, 5. So let me write, for example, a square root of 2 minus 3, 1 over 2, 3 over 4, minus 0.75. And then, for example, square root of 2 minus the square root of 3. Then I can have 0, 0, 1, and again 1, for example. So this is a rectangular array of numbers that you can see here. This is a matrix, and this is common, that you put these numbers in a rectangular array and that you enclose them by a pair of square brackets. But of course, sometimes in some books you see that they have used big parentheses. That's also possible, but I will use these square brackets to denote matrices. And then I can give it a name, and I can say that matrix A is equal to this object. And then you see that this object has 3 rows, yes, and it has 1, 2, 3, 4, 5 columns. And then this is also convention. The one on the top, the row on the top is called the first row, and this one is the last row. And the column on the left is called the first column, and this one is the last column. So this matrix has 3 rows and 5 columns. According to this convention here, I should say that this matrix is a matrix of order 3 by 5. 3 rows and 5 columns. So this is an example of a matrix. We can give you another example. I can give you another example. For example, B is equal to, I can write 1, 2, 0, minus 3, 7, 5, for example. This is also a matrix. This includes 1, 2, 3, 4, 5, 6 rows, but only 1 column. So that is a 6 by 1 matrix. I can have this situation. I can have 0 minus the square root of 2, 3 over 5, 0 minus 1, and 7. So that's also a matrix, but it only has 1 row and 1, 2, 3, 4, 5, 6 columns. So it is a 1 by 6 matrix. Yes? We can have this situation. So let me write here to save space. So for example, I can have this situation D, that I have 1, 0, 2, minus 1, 0, 1, 1, and 1. So you see, we don't have any limitation of the numbers that I can put as entries inside these matrices. Any number that you can see here, any number here, there, and there are called the entries of the corresponding matrix. Okay, here I have 1, 2, 3, 4 rows and only 2 columns. So this becomes a 4 by 2 matrix. Okay. So far, the numbers that I have used as entries are all coming from the set of real numbers, but that is not just a limitation. We can choose numbers from complex numbers. So for example, if I want to give you an example, I can give you an example here. For example, 0 minus I, and 0. Yes, this is also a matrix. There are 2 rows and 2 columns, so this is a 2 by 2 matrix. Yes, the number of rows and the number of columns are exactly the same here. And then this I is the famous imaginary unit. I squared is defined to be minus 1. And by the way, there is a name for this matrix in physics. This is one of the Pauli matrices. It arises in the context of quantum mechanics when people want to formulate the spin of an electron. So this matrix is a famous one. This is the second matrix in the set of triple matrices. Yeah, so we have three matrices. One of them is this one, and this is called sigma sub 2. And as you see in physics literature, they denote it by this lowercase Greek letter sigma. And sometimes, of course, in physics literature, you can see they write it as sigma sub y. Both of them refers to the same matrix that you see here. And as I told you, let me write the name of the scientist, physicist actually. He was a physicist, Pauli. So these are called Pauli matrices. This is one of them. So the reason that I brought this up is just want to mention that there is no limitation for the numbers that you can choose as the entries of your matrix, even though most of the time we only consider with real numbers. Okay. Okay. Now the second thing that we want to know, because later we want to prove a lot of theorems about matrices, and having a very shorthand, very compact and nice notation would be very handy. Yes, so it will help us a lot. And you know that if I have big matrices, writing them in general, it would be hard. So let me introduce you some ideas so that we are able to have a very shorthand and compact notation of a matrix. So assume that A, for example, so capital A, let A be an m by n matrix. So this means that this matrix includes m rows and n columns. Okay? So I would write it something like this. So what you expect is a rectangular array consisting of m rows and n columns. Yes? This is convention that if I denote the matrix by capital letter A, then I will choose lowercase letter a to denote, in general, the entries of that matrix. So for example, the first entry, I would write it little a, but of course, I need two indices to locate the position of this first entry. This entry is sitting on the first row, so I put an index 1. And because it is also sitting on the first column, so I will also add 1 here. So this is called A sub 1, 1. It means that the entry of the matrix denoted by capital A, which is sitting on the first row and on the first column. Yes? So this is also convention. The first number refers to the row number, and the second number refers to the column number. For example, if I want to denote the next one is still on the first row, so this index is still 1, but because now it is on the second column, we put a 2 here. And the next one would be A1, 3, and then if you continue, the last one here is still on the first row, but it is on the last column. And because I have assumed that this matrix is an m by n matrix, this the last column is column number n. So then I would write it as A1n. And then if I go to the second row, then I will have A starts with 2 because this is on the second row, but it's still in the first column. So it is A sub 2, 1. And the next one would be A sub 2, 2. And the next one, A2, 3. And then you continue up to A2n. And then you can continue these rows and then reach to the last row. Which one is the last row? I have assumed that my matrix is m by n, so it contains m rows. So it means that the entry here starts with the m, denoting that this is on the mth row. And this is still on the first column, so I put a 1 here. The next one would be AM2, the next one would be AM3, and of course, if I continue, the very last one would be MN, A sub MN. Yes, the mth row, the entry on the mth row, and on the nth column. So if I want to write this all the time, you see that if I want to talk about a matrix in general, I need to write a lot. So most of the time, we don't really need to write a lot, so we compact this and write simply this. We simply write this is equal to, we put a pair of square brackets here, and I put A sub ij, and then I would write m times n. So by just looking this, when I write A is equal to Aij mn, what I mean is that A is a matrix, it contains m rows, it contains n columns, and the entries are generically denoted by A sub ij. If I ask you what is this one, you would say that this is the entry sitting on the ith row and jth column of the matrix A, capital A. So then it would be easier to work with this symbol and notation rather than this one. Okay, so these are actually minor things, but it becomes very important. Okay, one thing, a remark that I want to mention here is that a 1 by 1 matrix, so let me write any, not to get confused, any 1 by 1 matrix is identified with its own, with its entry. With its only entry, actually. There is only one, because that's 1 by 1. So what does it mean? It means that if you see this matrix, for example, containing a square root of 2, you can just identify it with the square root of 2. Yes? So in general, if you have a matrix A, you can identify this with A itself. Okay, now we go to some examples. These examples are actually very simple, but the idea is that you get used to these notations and conventions that we are using here. So let me write an example here for you. Write out the matrix, for example, capital A equals to Aij, I would write 2 by 3, such that Aij is equal to I squared plus 3j. Yes? So what is this one? So I told you that this is a very simple example, but let us do them, okay? So this A is a 2 by 3 matrix. Its general entry is A sub ij. And then this is defined to be in this form. So A sub ij is equal to I to power 2, the index related to the row to power 2, and then the j index times 3 and add it together. So that is the rule that you can read it here. So now, because this matrix is a 2 by 3 matrix in general, what should I have? I have A is equal, this is a 2 by 3 matrix. It contains 2 rows and 3 columns, so it should be of this form, A11, A12, and A13. And then I will have A21, A22, and A23. So this is in general a 2 by 3 matrix, yes? But now there is a rule how to calculate them here, given in the problem itself. So what can I do? I can just write, here the row index is 1, so 1 to power 2, because row index is supposed to raise to power 2, and then 3 times the column index. And the next one is the row index to power 2, which is still 1, but this time 3 times the j index here is 2. And then the next one is similarly. Yes, and then I go to the next row. The next row, the I index is 2, so it becomes 2 to power 2 plus 3 times 1. And then I will have 2 to power 2 plus 3 times 2. And then finally, I have 2 to power 2 plus 3 times 3. Yes? And then you calculate them. So it's easy. So 3 plus 1 is 4, 6 plus 1, 7. This is 10. And then here I have 3 plus 4 is 7. And 6 plus 4 is 10. And then here 9 and 4 is 13. So this is the matrix that I am supposed to write for this one. Okay? Okay, now let me go to the blackboard to write another example here for you. So example, So write out the matrix. So let me call this one capital X with small xij, and let us this time make it 3 by 2. Write out the matrix this such that, so we have this definition. Xij is defined to be I minus j if I is less than or equal to j, and this is, for example, j over I if I is greater than j. Yes, this is essentially the same problem, but this time the rule for the entries follows two different rules. One of them, if this is happening, then the row index minus the j index is the answer if the row index is smaller than or equal to the column in j index, and if the row index I is greater than the j index, column index, then I divide the column index by the row index. Yes, so what can I do? I can just simply write the capital X is equal, because this is a 3 by 2 matrix, so it contains 3 rows and 2 columns. So the generic form of that is x11, x12, the next one x21, x22, x31, and x32. Okay, and now I need to use the formulas given here to be able to simplify that. So here 1 and 1 are the same, so I have to use this rule because this is acceptable if I is equal to j. And then I need to subtract them. So I will subtract 1 and 1 here. This is the first entry. The second entry, I is 1, j is 2, so still I should use this rule, so it is 1 minus j, which is, so it is 1 minus 2 because it is I minus j. But when I go here, the row index is 2, the j index is, the column index is 1, and this is bigger than that one, so I need to divide the j index by the I index. The j index here is 1, the I index is 2. And the next one, 2, 2, exactly again follows this rule. I need to subtract them, so it becomes 2 minus 2. And then finally, for the same reasons, x31 is 1 over 3, and x32, still the row index is greater than the column index, so I need to divide the column index by the row index, so it becomes 2 over 3. And of course, I can simplify this. 0, negative 1, 1/2, 0, 1/3, 2/3. Yes? So that's also something I want you to know. Let me give you another example. Just getting used to this notation. So example, for example, let A be this matrix. So 1, 2, 0, minus 1, 3, 2, 1, 1, minus 1, 1, 0, 0, square root of 2, 3, and 1. Yes, for example, this is a 2 by 1, 2, 3, 4, 5 matrix. Evaluate this expression. So these double sums are important, so let me just look ahead a little bit and to make ourselves ready for these calculations. Evaluate sigma and sigma, another sigma. I would write here aij, and then, for example, I goes from 1 to 3, and j goes from here to 1 to 2, for example. So I want to evaluate this. Okay, this is in the context of matrix theory. This is a 3 by 5 matrix denoted by capital A. In the same problem, you can see A sub ij, so definitely this doesn't need any more explanation. This means that the entries of this matrix, yes? So here the double sum, for example, if I want to evaluate that, so this means that I can write it in this form. So this is sigma, and then I can, in principle, I can assume that I am doing the inner sigma first. Of course, it doesn't matter which one you are doing. And then I would write j goes from 1 to 2, and then I goes from 1 to 3. Yeah, so you can interpret it in this way, or the other way around. I will talk about that one as well. So here I need to apply the first summation, and then after that is finished, I apply the second summation. Yes. So here I keep this summation as it is. So I just copy and paste that part, but instead of this expression, I can expand it. This expression depends on two indices, I and j, but the counter of the sigma only depends on j. So it means that I am not allowed to touch I, so I will keep I as it is, but then I will replace j with the first value, which is 1, and then I do the same thing. I keep I the same. I replace j with the second number, which is in this case the last number, and then it becomes 2. Then I will add them. So this is the expansion of the first inner sigma. And then I need to apply the second sigma here. But the second sigma, of course, you can use the properties of sigma and to expand, to write the sigma on the first one plus the sigma on the second one. But let us forget about those things, just expanding the sigma based on the definition of the sigma. So this is at the end some quantity depending on one index I, and that index is the counter of the sigma. Yeah, so I can just expand. How? I replace I everywhere by the first number here, which is 1. So I will replace I with 1. It becomes A1, 1, A1, 2. So this is this expression for I equal to 1. Then I put I equal to 2. So it becomes 2, 1, 2, 2. Then I would put finally the last one, which is A3, 1 plus A3, 2. And because of the sigma, I have to add these quantities. Yes? And now it's very, very simple. So this matrix is given here. A11 is this entry, which is 1. A12 is this entry, which is 2. And then A21 is 2. The next one is 1. And the next one is 0 and 0. So if you add all of them, so it becomes 6. So the answer is 6. Okay, very easy. But let me evaluate this sigma in a different way. So let me apply the first sigma here. I can write it in this form, but I can expand the first one here. Because you see, assume that you applied this first sigma. This index j is running from 1 to 2, so there is only dependence on I left. Because I'm running over j, so the dependence is light. So you can consider this expression in brackets as something which depends only on I. So this, I can call it lambda sub I. Lambda is just a symbol, but this, I'm just by writing lambda I mean that this expression is an expression depending only on one index. It's very important to understand. And this sigma has the right counter. Yes, the counter is I. This index is also I, so I can sum it over. So if I want to apply this one first, this means that I can write lambda 1 plus lambda 2 plus lambda 3. But of course, what is lambda 1? Lambda I is this expression, so lambda 1 means that I need to replace I with 1. So this becomes sigma A1j. J goes from 1 to 2. And the next one plus lambda 2. Lambda 2 means that I need to replace I with 2. So this becomes the same structure. J goes from 1 to 2. The same structure, only the difference is that I replace I with 2. And then finally, I will have this one. Yes? And then if you realize, you can see that this is exactly, if I open it, this becomes the first one. If I open this one, it becomes the second one. And if I open this one, it becomes the third one. I will get the same values. I will get the same value. Okay. So something, for example, let me give you another example here. Let me write it here, and then I will continue there. So example. Let aij's be numbers depending on two integers I and j, such that, for example, I goes from 1 to m is also a positive integer, and j goes from 1 to n. Yes, show that. So we want to show this. We want to show that sigma of a sub I goes from 1 to m, and then j goes from 1 to n, is the same quantity, is the same number if I interchange these summations, meaning that first I run j from 1 to n, then I will run I from 1 to m, as I, j. Yes? So here, I want to show that this is the case. If aij, I don't know anything about aij, except that I know that these are some quantities which depend on two integers, say I and j. Yes? So what does it mean? It means that if I have a double sum, one summed over a counter I, the other is summed over another counter j, I can just replace them. Yes, I can interchange these two summations. Okay, so one way to look at this problem is to arrange these numbers with two indices in a matrix. Yes? So it's clear that I can arrange these numbers into a rectangular array. Yes, it becomes A11, A12, up to A1n, then the next one A21, A22, up to A2n, and finally AM1, AM2, up to AMN. You see, I gave you MN numbers because the number of entries here is MN. This has nothing to do with matrices. These are just quantities depending on two integers, I and j. But now I'm saying that prove this, which is something in the sigma, a property of sigmas. And then to prove this, I am saying that, okay, one way to look at this problem is to arrange those numbers that depend on I and j in a rectangular array. But we have a name for this rectangular array now. It's a matrix. Let me call it matrix A. Okay, so then I will calculate the sum of numbers in this array in two different ways. But because I am calculating the same quantity in two different ways, it means that these two should match. Yes, and that is the way that I want to prove. For example, let us see what does this mean. So the left-hand side is equal to sigma. Let me keep this sigma first and then open the inner sigma. So then it becomes I from 1 to m. So what happens? The first one, I open it by running j from 1 to n. So it becomes ai1, the next one is ai2, and finally I reach to ain. This is when I open the inner sigma. Then I need to apply this outer sigma by replacing i's everywhere with 1, then replacing i's everywhere with 2, and continue until I reach to m and add all of these things together. So what happens here? This becomes A11 plus A12 up to A1n. And the next one, if I put it 2, it becomes A21, A22 up to A2n. And then finally, I continue until the very last one, which becomes AM1, AM2, and then I continue until AMN. But if you look in this list, it means that I am adding all these numbers, yes, in this way. So I am adding these rows. This is the sum of the entries on the first row. This is the sum of the entries on the second row. And finally, this is the sum of the entries on the last row. And when I add them together, it means that what I am calculating is the sum of all the numbers in this rectangular array. Okay, so this becomes equal to the total sum, equal to the total sum. But immediately you can convince yourself that if you calculate the right-hand side, it will also give you the total sum. Why? Because now the right-hand side is I have j goes from 1 to n, but now I open this sigma first, running I from 1 to m. So it becomes a 1j, a 2j, up to a mj. Yes? And now I start opening the second sigma by running j from 1 to n. So this means that I would write a11 plus a21 up to am1. Yes, I replace j with the first number 1 everywhere. And then I change j from 1 to 2. So it becomes a1, 2 plus a22 plus up to m2. Yes, and then I continue until the last entry, the last number n. So then it becomes a1n plus a2n plus up to mn. And now again, these are the same numbers, but here I was adding the numbers on each row first. This is the first row, second row, and the last row, and then I am adding the results. But now if you look here, a11 plus a21 up to am1 are the sum of the numbers sitting in the first column. So this sum is different from that sum, of course. But if you go to the next one, this is the sum of the entries on the second column. Yes? And if I go to the last one, these are the sum of entries of the last column. So it means that again, you can easily convince yourself, it's completely clear that again, I am calculating the total sum. So this is also equal to the total sum. Yes? So the order of calculating is different. Here, first I add on rows, then I will add on columns. So I add horizontally first, and then when I get these results at the end of each row, I add vertically. But in the second one, I add vertically first, and I get these numbers at the end, and I add horizontally. But of course, it's clear that I am calculating the same quantity, so it means that the total sum both of them are equal to the total sum, so it means that they have to be equal to each other. So from now on, whenever we want to interchange two sigmas, we're allowed to do that because we have the proof here. Okay, so one important thing when working with matrices is actually some terminologies, some different types of matrices that we freely use when we are teaching, we are working in linear algebra. So I want to introduce those to you, okay? So let me give it a title. So different types of matrices. So that's also very important to know. So the first matrix that I want to talk about, so these are the terminologies that you need to know. One, row matrix, row matrices. So a row matrix is clear from its name. It's a matrix containing exactly one row, not more. Yes. So any matrix of this form, A, for example, 1, 1, A, 1, 2, and then up to A, 1n is a 1 by n matrix. That is a generic row matrix. So a row matrix is a matrix having exactly one row. And then, of course, you can guess what comes next. That is a column matrix. And that is a matrix having exactly one column. For example, B is B11, B21, up to, for example, BM1. This is M by 1 matrix. So it has only one column. This has only one row. Okay? And the next thing is the zero. So zero matrices. So zero matrices. So what are zero matrices? Zero matrices are the matrices that have all their entries equal to 0, but they can have different orders. Yes. For example, this is a zero matrix. Yes, but it is 2 by 1. This is also a column matrix here. Or we can have this zero matrix. This is a 2 by 2 zero matrix. This is usually denoted by capital letter O, and then you write the order here. Of course, if the order is not important, you just simply write O. Yes, and then here, this is the zero matrix, but 2 by 2. Yes, so you can have different zero matrices. We have infinitely many zero matrices. What they have in common is that the entries are all 0, but they can have different orders. Okay. Okay. Now let me open some space here. So another important class of matrices are square matrices. So number 4, square matrices. So it's clear, it means that our rectangular array is now a square, yes? So it means that the number of rows and columns are the same. So that is the meaning of being a square matrix. For example, A equals to 1, 2, 3, 0, minus 1, 5, square root of 2, 0.51 is a square matrix. 3 by 3 square matrix. When a matrix is a square matrix, instead of saying that this is a 3 by 3 matrix, we say this is a square matrix of order 3. So A is a square matrix of order 3. This is also one way to express this. You can of course say that this is a 3 by 3 matrix or a square matrix of order 3. So for example, the Pauli matrix that I mentioned earlier, sigma y, is a 2 by 2 matrix, which is a square matrix, and that is also a square matrix of order 2. But what is important when it comes to square matrices is the diagonals of the square matrix. Yes? So we say that these entries here form the main diagonal of this matrix. So the entries on this diagonal are called the entries on the main diagonal. So this is the main diagonal. And then entries on the other diagonal are called minor diagonal. The entries of the minor diagonal. So I want you to know about this. But don't get confused. The notion of diagonal even makes sense if you have a rectangle, yes? In geometry, if you have a rectangle, still, this is a diagonal that is also a diagonal. But remember, the notion of a diagonal in matrices only makes sense if I have a square matrix. Okay, so that's one point you need to remember. So we are not allowed to talk about diagonals when I have really rectangular matrices. Okay, so here the main diagonal are all of them 0 and 0, and here the minor diagonal elements are minus I and I. Okay, so let us talk a little bit about that. What is the property of the what is the generic property of entries lying on the main diagonal? Yeah, it is easy to guess. The number of row is exactly to equal to the number of column. So here, this entry is sitting on the row 1, column 1. This entry on the main diagonal is sitting on the second row, second column, and this one is sitting on the third row, third column. So in general, the form of the entries here, you can write it as A sub ij and say that I is equal to j, or you can simply write A I. Yes, I goes from 1 to 3, for example, here. So this is the property of the elements on the main diagonal. And what happens here? If you don't mind, let me just mention it in a generic matrix here for you. So if I have A11, A12, A13, the next one would be A21, A22, A23, then A31, A32, A33. So you see that the entries are 1, 1, 2, 2, and 3, 3. But here, what is happening? Let us check. This is 1, 3. This is 2, 2. This is 3, 1. The property is that if I add these indices together, so here I will get 1 plus 3, it becomes 4. Here, if I add 2 and 2, it becomes 4. Here, if I add 3 and 1, again, it becomes 4. Yes? So it means that this the sum is a constant, 4, 4, 4. And 4 is exactly 1 unit more than the order of this matrix. This matrix was order 3, so this is 3 plus 1, which is 4. Of course, I am not proving them. I am just trying to draw your attention to it. These are very simple things, and you can just do them yourself, yes? So let me just give you this picture in your mind. It is good to have it. So if I have a square matrix, then this is let me draw it with a different color. So if I have this square matrix, okay, then the entries lying on this diagonal here, 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 this is called the entries on the main diagonal. What are the properties here? The row index is equal to the j index. And what is the property of the entries above the main diagonal? Look here. So this is my diagonal. This is the main diagonal. You see, the row index is always smaller than the j index when I am above the main diagonal. 1 is smaller than 2, 1 is smaller than 3, even 2 is smaller than 3. So here, this region is the region that the row index, usually we denote I, we denote the row index by I, if you don't mention it explicitly otherwise. So I is smaller than j, and this is I greater than j. If you see, these are, in these cases, the row index is greater than the j index. And if I want to go draw something similar to this for the minor diagonal, so this is again a square matrix. So the minor diagonal is this one. What is the property here? If I add these two indices, it becomes n plus 1. So let me write this square matrices of order n, square matrix of order n. It means that this is n by n matrix. And then here, what will happen? So here, if you are above the minor diagonal, if you add these indices, it is smaller than n plus 1 for 2 plus 1 is 3, 2 plus 1 is 3, 1 plus 1 is 2. So here you have I plus j is smaller than n plus 1, and below the main diagonal, I plus j is greater than n plus 1. Yes? So this is a good picture to have in mind when you are dealing with square matrices. As let me mention, diagonals only make sense if you're dealing with square matrices. Now I want to talk about particular special cases of square matrices. That's also very important. So now square matrices also are divided into different types, so which are important to talk. So let me write this number 5. This is called upper triangular matrix. Upper triangular matrix. matrices. And then number 6, lower triangular matrices. So let me define them for you here. Upper triangular means that you have a square matrix, and assume that this is your main diagonal. This is your main diagonal. When everything below the main diagonal is 0. So let me put a big 0, meaning that every entry that you see below the main diagonal is 0. Then you call it upper triangular. So it means that you don't know exactly what is going on here, but you know that all these numbers are equal to 0, so you call it upper triangular matrix. But then in this situation, you have the square matrix. Again, upper triangular matrices and lower triangular matrices are square matrices in the first place. So then, in this case, if everything above the main diagonal is 0, then this is called lower triangular. So this adjectives upper and lower doesn't refer to the zeros, they refer to non-zeros in principle, okay? But I'm not saying that these are non-zero. What I'm saying is that above the main diagonal, everything is 0, it's called a lower triangular. Below the main diagonal, everything is 0, it's upper triangular. Okay, so for example, if I want to give you some examples here, so here, this is an example of a 3 by 3 upper triangular matrix. So for example, 1, 2, 3, then I can have 0, 7, 1, then I can have 7, 7, minus 1. So this is an upper triangular matrix of order 3. Why? Because if you consider this as the main diagonal, everything below, you see I have a block of zeros there. So that's an upper triangular matrix. So you see, if I change this 7 to 0, then still it's an upper triangular, because what I care about being upper triangular is why just cover everything. I only care about the entries below. If all of them are 0, then I just immediately say that this is an upper triangular matrix, even if there are other zeros somewhere else. For example, I don't know, for example, if I have this matrix 0, 0, 0, 0, this is still upper triangular, yes? Because if I just cover this matrix and concentrate on the entries below the main diagonal, everything, which is the same, only one here, it's a 0, it means that this is upper triangular. But of course, this is also a lower triangular matrix, yes? If I just cover this one, I don't look at the entries below the main diagonal, only concentrate here, that is always 0 here. So this means that this is both upper triangular and lower triangular. So this is very important. Don't confuse yourself that these are not allowed to be zeros and everything, okay? For example, I can also write another example. So 1, 2, 3, and then I put 0 here, 0 here, 0 there. Yes, so that is both upper triangular and lower triangular. It is upper triangular because if I just look below the main diagonal, everything is 0. It is lower triangular because if I look above the main diagonal, everything is 0. These kinds of matrices have a specific name. These are called diagonal matrices. Yes. So number 7, if I want to add it here. So number 7 is called a diagonal matrix. So 7, diagonal matrices. Yes. So a matrix, something like this. We have, for example, D11 here, D22 here, up to say DNN, if that's an n by n matrix. And everything here is 0, everything here is 0. It doesn't necessarily mean that none of them is 0. Some of them can be 0, even all of them can be 0. And there is another notation for this diagonal matrix. We write it as diag and then I put the entries here, D11, D22, up to DNN. That's also one notation that is sometimes used in the literature. So for example, if I tell you diagonal of 1 minus 2 square root of 3, if you see this, it means that you are facing a 3 by 3 matrix, which is diagonal, and these are the entries on the main diagonal in order. The first one is 2, the second one is minus 2, the last one is the square root of 3, but everywhere else is 0. That is the meaning of this symbol. So upper triangular matrices, lower triangular matrices, and diagonal matrices are very important type of matrices that we will deal a lot in this course. And then finally, if all of these numbers sitting on the main diagonal of a diagonal matrix, that matrix is called a scalar matrix. Yes, so scalar matrices. So for example, I can say this, 2, 0, 0, 2. This is a scalar matrix. First, it is a square, it is diagonal, and any entry on the main diagonal is the same value 2. So that's a scalar matrix. Yes. We can have, for example, diagonal square root of 3, square root of 3, square root of 3, square root of 3, even though it is diagonal, but because all these entries are exactly the same, that is actually a scalar matrix. Okay. And finally, the last category is called identity matrices, which actually play a vital role in the theory of matrices. Identity matrices. Okay, so identity matrices are scalar matrices for which all the entries are on the main diagonal are equal to 1. So for example, and then for example, 1, 0, 0, 1. This is an identity matrix of order 2. For example, this one, 1, 0, 0, 0, 1, 0, 0, 0, 1. This is an identity. This is the identity matrix of order 3. The identity matrix of order 1, of course, includes only 1 so that you can identify it with 1. Yes? And the letter I usually is reserved in the theory of matrices for the identity matrices. And then you put an index below them to show the order. So for example, I1 means that the identity matrix of order 1, which is just 1. But this one is identity matrix of order 2. And this one is the identity matrix of order 3. Okay? Okay, so you will see that later, the reason that we call it identity, because it plays the role of identity element in matrix multiplication. So if that multiplication with an identity matrix is defined, then it will not alter the matrix at all. That's why this is called identity matrix. We will come to these things later. So these terminologies are very important to know about them, because you will face them in problems in the context of theorems and everything. So it's very crucial to know these names by heart. Okay, but let me just finalize this session by introducing you a very handy and useful symbol called Kronecker delta. Let me just clean this part. Yeah, we can start from here. So, definition. The symbol, where this delta is the lowercase Greek letter delta with equipped with two indices I and j, where I and j are coming from the set of positive integers, the symbol delta ij, where I and j belongs to the set of positive integers, yes, which is defined as follows. So it doesn't look impressive, but you will see that we will use it quite a lot. So it is defined as follows. Delta ij attains two values, takes two values, either 0 or 1. It takes value 0 if these two indices are not the same, and it is defined to be equal to 1 if these two indices are the same. Okay? This symbol is defined as follows. It is called the Kronecker delta. Okay. So one thing that you can immediately realize, for example, if I ask you what is delta 1, 1, if I ask you what is delta 3, 3, if I ask you what is delta 7, 7, you always say 1, because 1 is equal to 1, 3 is equal to 3, 7 is equal to 7. But if I ask you what is delta 2, 3, you definitely will tell me 0, because by definition, if I and j are not equal, then you can say 0. Delta 3 and 2 is also equal to 0, and then you can continue as likewise, yes? So in principle, it is very clear that this is a symmetric symbol with respect to the interchange in I and j. So it means delta ij is exactly equal to delta ji, and then it doesn't matter if I raise this delta ji to some power n, for example, any power, integer power, for example. Integer power, if it is negative, it does not work. So let us be on the safe side. If I have a positive if I have a positive exponent, then delta ij to that power is equal to delta ij itself. Because if I and j are equal, the left-hand side is 1 to power n, which is 1. The right-hand side is also 1. If I and j are not equal, the left-hand side is 0 to power n, which is 0, and the right-hand side is also 0. Okay. What is the benefit of this? The good point about this, well, let me first give you an example using this idea of the Kronecker delta. Okay. So, for example, let us simplify this expression. Assume that you have a sum. Inside the sum, you have a sub ik, and then you have delta, say, k5, and then k goes from 1 to, say, 6. So, how should I simplify that? It's very simple. These kinds of sums will appear a lot in matrix theory. So this is why I'm looking ahead and then try to equip ourselves with these ideas so that we can use them later very quickly. So here it means that if I want to write this sum, in principle, I should expand this sum. It becomes AI1 delta 1, 5. The next one is AI2 delta 2, 5. The next one is AI3 delta 3, 5. And the next one is AI4 delta, oh, sorry, this is delta 3, 5 plus AI4 delta 4, 5 plus I5 delta 5, 5, and then finally AI6 delta 6, 5. Yes. But then these are all zeros because 1 is not equal to 5, 2 is not equal to 5, 3 is not equal to 5, but only one term, here will survive because 5 is equal to 5. So everything, regardless of the value of these a's, become equal to 0 except this term. So then it becomes ai5 multiplied by 1, which is ai5. So I don't want you to write this sum. Immediately, what is the point is that whenever you see a delta inside a sum notation, okay, such that one of the indices for delta is the counter of the sigma, and the second index is in the range of the counter of the sigma, what you can do, you can simply drop the sigma, you can drop this delta, and you write this expression which is left, but you need to replace the k counter with this value, the second value, which becomes a5. So this way of thinking is very handy in the future. So if you have a delta with two indices, delta have always two indices. One of them, if one of them is the counter of the sigma, and if the second index is in the range of the counter, this applies. If the second index is not in the range, then definitely it is 0. For example, if I wanted to calculate this thing, but assume that this time the upper limit is 4 instead of 6. So then everything up to here is actually 0. So this becomes 0, yes? Because we will never reach to that limit that we needed. So you might think that why I'm talking about these things. The reason is that later I won't just immediately quickly calculate them without mentioning anything. So this way of looking is very handy. Just drop the delta, drop the sigma, and switch this remaining counter by the second index of your delta. That's very good. I will give you some of these things in the exercises. Okay. For example, if I ask you to calculate this, if I want to give you an example, assume that you have this matrix A. So let me write 2, 3, 0, 1, 1, minus 1, 0, 7, 7, 1, 2, 1. And then I ask you to calculate this sigma. Sigma of A, for example, let me write 1k to power 2 plus 2a 1k. And then I have delta k3. And then here I have k goes from 1 to 3. So let me write it k2. Okay, now you see here you have a sum. Inside the sum you have a delta. One of the indices of this delta is the counter of the sigma, so everything is exactly as before. And this expression is something which depends on the counter as well. So what you want to do immediately, and then you see that the second index is in the range of the counter of the sigma. So what you need to do, you drop the summation, you drop the delta. So what is left is this expression. Yes, but then what you need to do is to replace k with this second index everywhere. So it becomes 1, 2, and here it's also 1, 2. And then you can read it from here. So x 1, 2, the first entry on the first row and the second column is this one. So this becomes 3 to power 2 plus 2 times 3, and then it becomes 9 plus 6, it is 15. So that's the answer to this example. Okay. So the reason that this chronicle delta becomes important in matrix theory is because I can write the identity matrix in terms of them. Yes. So here I told you that A, in general, if I have an m by n matrix, I can write it as Aij m by n. So sometimes we will write it like this. We will write the matrix A sub ij, and then I ask you what is this. You can answer this is Aij. So this means that I have the matrix capital A, and this notation means that I am interested in the entry ijth entry of this matrix. But you know that there is another symbol for this, and that is A sub ij. Now, if I tell you for the same reason, delta, this is the identity matrix of order n, then you can simply write it as delta ij n by n. Yes, because what was the identity matrix? For example, let us consider the 3 by 3 scenario, 3 by 3 case. So this is 0, 0, and 0, 0, and 0. So this means that if I have the entries here, they are 1. Why? Do you remember? On the main diagonal, index I and index j are equal. So this means that these are 1. But if I am here or there, the indices I and j are different, so it becomes 0. So if I ask you, what if I give you the identity matrix, and if I ask you what is the ijth entry of in, you can say that this is 1 if I is equal to j, it is 0 if I is not equal to j, but this is exactly the definition of delta ij. So this is very good to remember that delta ij in matrix theory is actually very useful when we are dealing with identity matrices. So that's a way to write this in a unified form instead of writing this in this form, saying that 1 if this, 0 if that. We can just simply write delta ij. You will see that this property, this definition, and this property of sigma, including the delta, Kronecker delta inside them, would be very handy when it comes to proving theorems in matrix theory. Okay, so I will stop here. You will find a link to the PDF file of the problems that you can solve based on the material that I covered in this lecture. Next time, I will actually record a video solving those problems and upload them. All these videos are being uploaded onto the playlist called Basic Linear Algebra on my YouTube channel. If you think that the videos are helpful, I would be very happy that if you can give me a thumb up and also subscribe to my channel. Until the next video, goodbye. Thank you.